Hello, my name is Rudolf Szadkowski. I am from Czech Technical University in Prague, and I will present to you the paper Neurodynamic Sensory Motor Phase Binding for Multi-Legged Walking Robots. Imagine you have such multi-legged walking robot, which is deployed in an unknown dynamic environment on a long-term mission. This robot will travel vast distances and it will encounter new unknown terrains with unknown dynamics, and since it is a long-term mission, its body will start to eventually decay. So the robot has to adapt these changes within environment and within its own body. Another thing is that the terrain itself will provide some disturbances since it is irregular, and the robot must be stable to these disturbances. The state of the art of such plastic and stable locomotion can be found in nature, where the animals have to deal with these challenges on daily basis. So this is why we want to get inspired by the animal solution to these challenges and adapt them into the robotic domain. One of such animal solutions for traversing vast distances is to use a gait. A gait is a repetitive motion pattern where the animal repeats some series of movements. However, it is not just about the repetition. The gait motion utilizes the sensory feedback, so it is able to react to terrain unevenness or to adapt some body changes or new terrains. Such complex behavior is controlled by relatively simple neural circuits which are located inside a spine. So there is a hope that the model of such locomotion control will be simple. In locomotion control, there are two systems to consider: the controller and the environment. The controller generates the commands for the actuators, so the robot can move. The state of the controller is described by the motor variables. Then we have the environment, which is perceived by the robotic sensors, and thus it is described by the sensory variables. The sensory variables provide feedback for the controller, so in case of some external disturbances, the robot is able to stabilize the motion. In context of the gait control, we can assume that the variables, both motor and sensory, have the same period. So the variables can be described in terms of amplitude and phase. This is also why most CPG-based controllers are decomposed into the amplitude control and phase control. In this work, we focus on the phase control. The phase controller generates the motion rhythm that synchronizes the motion with environment. During undisturbed gait, the phases of sensory variables and motor variables grow at the same rate. So we can observe that their difference is the same over the time. We call this difference the phase offset. This phase offset is static during the undisturbed gait. However, as the gait is disturbed, this offset can change in time as well. So by synchronization, we mean that the difference between the sensory and motor phases is stable at the phase offset. So as the motion gets disturbed, the synchronization will drive the phase difference back to its stable phase offset, as we can see in this illustration. To continuously synchronize our system, we need a continuous measurement of the phase of the motor and phase of the sensor. However, we only measure some events, such as the ground contact, which is discrete. We do not know what is the sensory phase between these discrete measurements. So we have to estimate the sensory phase in order to synchronize continuously. The nature provides us a tool for synchronization and estimation, the central pattern generator. The central pattern generator, the CPG, is a neural complex which is located inside animal spine, and it centrally generates rhythm of the actuation, the motor rhythm. It is usually modeled as a half-center oscillator, which is depicted here above. It is two inhibiting neurons, so only one neuron is active at the time, and this system has some interesting properties. First is that the activation of the neuron generates a stable periodic signal. Here in the picture on the right, we can see multiple initializations of the system, but they always in the limit approximate a circle, which is stable, and thus creating a stable periodic signal. Second property is synchronization. Here on the picture on the right, we can see a discrete periodic excitation, which is fed into the multiple CPGs. At first, the CPGs have different phases, they are not coherent, and as the time progresses, the peaks overlap, so they synchronize this exciting signal. And finally, after synchronization, we can say that the CPG signal estimates the phase of the excitation. So here we can see that the excitation is more or less discrete. It can be, for example, the event of the ground contact, and the CPG describes continuously the phase of this event. Now let's go back to the phase control task. There are two goals. First is to generate a correct actuator rhythm, and second is to synchronize the actuator rhythm to the environment. For that, we introduce two CPG types. First is the motor CPG, which generates the motor phase, and second is the sensory CPG, which estimates the sensory phase continuously. So now, to synchronize the motor CPG to environment, we have to synchronize the motor CPG to sensory CPG. So we have to connect the both motor CPG and the sensory CPG. Since there is one sensory CPG per sensory variable, we have to connect one motor to multiple sensory CPGs, because we have no prior knowledge about the morphology except for the number of actuators and sensors. However, as we have seen in the previous slide, we can safely entrain the CPG, we can safely synchronize the CPG to only one periodic pulse. So now we have a problem that we have to somehow transform the activity of multiple sensory CPGs to only one exciting pulse. So we have multiple sensory CPGs. In this case, on the illustration, we can see three, where each sensory CPG estimates continuously the phase of the sensory event and has its own activation. We have to somehow find a way how to transform these activations into one exciting pulse, which is fed into the motor CPG. For that, we introduce a binding neuron. A binding neuron is a special type of neuron which is trained to peak during a given time window. So each sensory CPG gets their own binding neuron, and the neurons altogether are trained with a shared time window. So when they peak together. The activity of the binding neurons is there added together, and the sum is then the exciting pulse, which is fed to the motor CPG. And thus the motor CPG synchronizes to sensory events. However, it is essential to train binding neurons during a regular undisturbed gait, because the binding neurons actually encodes the offset between the sensory CPGs and motor CPG. So in order to get the regular offsets, we have to train the binding neurons during the regular gait. We implement the binding neurons as a RBF neuron, which is trained by a periodic Grossberg rule, described in detail in the paper. So now we generalize the architecture for multiple actuators. So each sensory variable and motor variable has their own CPG. Here on the picture we can see that we have 3 sensors, which have thus corresponding 3 sensor CPGs, and 2 actuators, which have corresponding 2 motor CPGs. We can then organize our architecture into 4 layers. First layer is the sensory CPGs, which estimates continuously the sensory phases. Second is the sensory RBFs, which learn the offsets between the sensory CPG and motor CPG. Then we have the motor CPGs, which generates the periodic signal for the phase control. And finally, a new layer is the motor RBFs, which bind the motor CPGs to actuators. The phase control is then fed into the amplitude control. In this work, we modulate the phase control into the angular velocity control for each joint. We have deployed our controller on a Phantom X robot, a hexapod walking robot which is depicted here. And we trained this robot to walk the tripod gait. As we can see, this robot has multiple joints, from which we control only the coxa joint, which is connected to the robot's body, and the femur joint, which is connected to the robot's femur. So we control in total 12 joints. Therefore, we need 12 motor CPGs. Moreover, for each leg, we measure 3 different events, such as ground contact or leg position. So we have in total 18 events which we measure and which we estimate with 18 sensory CPGs. Therefore, the learning task is twofold. First is to generate the desired phase control, dt, and second is to learn the phase offset between each sensory and motor CPGs. As we can see at the top, the phase control, which is depicted as the green and blue signal, does not align the target control, dt, which is depicted as the black pulses. However, as the learning progresses, the phase control aligns the target control. Moreover, at the middle, we can see how the system learns the offset between the motor CPG and sensory CPG. Each sensory RBF neuron finds their respective phase offset. And if we take cosine similarity of found weights, we can see that the joints that move at the same time have the same weights. This system was learned within 3 minutes. As we can see here, the hexapod robot was able to walk the tripod gait. In this next experiment, we demonstrate the synchronization which is provided by our controller. On the right, we can see the control signals coxa and femur. At a certain point of time, which is marked by the vertical red line, the front legs are forced to shift the phase. The control signal of the front legs is shown in the black color, and the other legs, shown in the green color, should somehow synchronize the forced control. It is, however, impossible to synchronize without feedback to the phase controller. As we can see here on the top, control stays desynchronized all the time. Our proposed controller is able to synchronize the forced control since it picks up the change in the sensory variables, and since the controller is synchronized to the sensory variables, therefore it synchronizes to the forced control, which we can see here that the control signals overlap. This concludes our presentation about our plastic phase controller. In the future work, we want to combine our plastic phase controller with amplitude learning and thus obtain the full gait controller. Moreover, we want to utilize the sensory and motor phase CPG estimations for phase-dependent reflexes. Thank you for your attention and goodbye.